So we've discussed JFETs, and they're really easy to use. I would argue they're even easier to use than BJTs. In my personal opinion so far, at my current low skill level, it's a whole lot easier to control voltage than it is to control current. So a voltage-controlled device is a lot easier to use than a current-controlled device, although BJTs certainly can put through a whole lot more power. So I look at JFETs more as a logic item, or a digital switch item, for something inside a logic system, rather than any sort of control for something bigger like a motor. But there's one wrinkle that I mentioned, which is the resistor across the gate-to-source connection. Basically, you need it for JFET function. So without getting into physical details, which are a little complex, let me just show you with an actual JFET what happens if you do and don't. So I will turn my power supply on. It will be on 5 volts, and I'll go ahead and turn it up to 10 milliamps just so it's supplying the actual voltage. That will be one supply. Recall how I said that it's easy to power a JFET, to operate a JFET if you're using 2 different supplies? That's what I'm going to do. I'm going to have one supply that's going across drain to source, and one supply that's going across source to gate, so that I don't have to worry about any sort of weird wiring. My second power supply will be a 9-volt battery, connected to a barrel jack, with a breakout. Nice and easy. So positive and negative there. So the first thing I'd like to show you is that the JFET is, by default, on. And remember how drain and source are interchangeable as long as your spec sheet says it is? This one says it is, so the nice thing is I only have to remember where the gate is. If I have the flat side, this is the TO92, so you've got the curved side and the flat side. If I have the flat side to the left, then I know that the bottom pin is the gate, and then the other two, I just pick whichever I like more. This chip is the 2N5457, and it's nice. It's got, let me see if it'll focus. It might focus, but the pins, there we are. You can still see it. The pins, perhaps now you can see it, are bent out a bit to fit in a breadboard. They have a little wiggle at the top. That might have focused. I'll find out later. So I will connect from positive of the battery into this one. I'm deciding that is my drain. I will go out the one I decide is my source, so I'm ignoring the gate, and I'm going through an LED. You'll notice I'm using no resistor. I looked at the spec sheet for this. The typical outputs are on the order of 1 to 5 milliamps IDSSSS, so I'm definitely not going to get too much current. And it's rated for up to 25 volts across it. So I've got 9 volts, and it's going to put out perhaps 1, perhaps 5, perhaps 2 or so milliamps. So I don't need a resistor. So I'll connect it to the negative of the battery, and the LED comes on. Disconnect, reconnect. So without anything else, without anything across the gate, there we go. It's normally on. So let's actually measure this current. Put it on the 20 milliamp setting, make sure it's on camera, lament how much work I'm going to have to do to clean this table, and now I will connect the probe through the LED to the negative battery, and it's drawing about 3 milliamps, as we would expect. Now, let's actually operate this properly. In fact, I'll go ahead and leave that as an amp meter, because the gate current is going to be minuscule. So this is the only current there really is to measure. This is ID, the drain current. So I will now use the power supply, the bench power supply. I will connect from the positive of the bench power supply to the source. And all of a sudden, we seem to have a problem. We have quite a fluctuation. It drained and it's slowly going back up, and then it's going back down. There's funky things happening. Because even though I don't have a circuit, I've got charges. This is voltage controlled. There's weirdness with charges. But I will now connect the gate. See, another wire. Now it's messing up even more to the negative. And now it turns off. That's correct, because this is a depletion mode device. And so applying a voltage across, you can see it's drawing minuscule current. Applying a voltage from source to gate, so gate to source would be negative, turns it off. I'm applying 5 volts, that's definitely going to be plenty. Now, you say, okay, well, let me stop doing that. Let me go ahead and remove that circuit. Comes back on, but it's only doing 0.8, and now it's up to 1.4. 1.3, now it's going back down. 1.6, 1.4. What in the world is going on? But it's nice and stable when I do that. So what if I connect ground to ground, comes on 2.47, go back to that. What if I connect positive to positive? That's no voltage again. So it's working. It is working without that resistor, but we're getting some weird values. And if I just disconnect, look at how long that took. That was over a second. Only when we have a proper connection is it working at all. But now, I will connect a resistor, which I believe is 10K. No, I've got a 1K, but that's good enough. I have a 1K resistor that I'm going to connect across gate to source. So there's a wire for source into one end of the resistor and a wire from gate to the other end of the resistor, and nothing happened because I'm applying that voltage. But now, if I remove the voltage I'm applying across source and gate, it instantly snaps up and it's nice and well behaved. Put it back in, take it out, and we have a nice fast response, a nice stable number. What if I remove the current entirely, or rather the voltage? See, that works fine. So we've stabilized it. We're getting nice, even results. So what happens if I've got this set up and I remove the connection to the resistor? Nothing. Let me put it back in. Let me remove the voltage. So now I just have a cross drain to source. So let me now disconnect the resistor. 1.8, 1.6, 1.3, 1.0. There is no voltage across gate to source. That's disconnected. I'll even remove the other one. Oh, look, that did something. Put that back in. Weirdness. Weirdness. I'll now reconnect the resistor. Connect, disconnect. So, as you can see, the JFET is absolutely functional without that resistor. But it's functional in the same way that a car with underinflated tires or even flat tires is functional. You can get it to go. You can drive it. But it's not doing what you want it to do. But with that resistor, then you can connect and disconnect whatever you want, however you want, and it'll behave nice and beautifully. So as I said, without going into deep physical details, which could be its own video, I'm sure, the point is, for that JFET, put that resistor on there. It essentially allows the transistor to equalize itself. Sort of like a shunt, I suppose. And the size of the resistor affects the responsiveness. Smaller resistor, more heat generated, faster response. Larger resistor, less heat generated, slower response. So if you're doing simple switching on something that's operating at human timescales, feel free to stick a gigantic resistor on there. 10K, maybe even 100K, give it a shot. 10K will probably be plenty, I'm sure. We're not dealing with 80 volts here. For faster response, well, 1K seems to work. You could maybe even go with 100 ohms. You'd have to test to see how much heat is generated. My spec sheet lists a maximum of 10 milliamps gate and source current. Now, that source current, as far as I can tell, wouldn't be going through the gate technically. I am assuming, from what I understand so far, that it's referring to this equalization current. So if you had 5 volts, you could figure out what resistor to get down to 10 milliamps or less. But in any case, that's just a quick demonstration to show you, just put the resistor on and then you don't have to think about it. But that'll do it. So until next time, I'll be seeing you.